Hello, welcome back. The title of this lesson is called Newton's First Law of Motion. Now, of course, you all heard of Sir Isaac Newton. He proposed and put forth his famous 3 laws of motion in the 1600s. They are every bit as applicable today as they were then, and they really form the cornerstone of essential core physics that you have to learn. Now, the good news is they're very easy to understand, but the bad news is everybody has their own idea of how they work. Usually it's not quite right until you take a class in physics and really try to break them down. So in this lesson, we'll talk about Newton's first law of motion. Later on, Newton's second law. Later on, Newton's third law. Just keep in mind that they're all kind of intertwined. They're all related to how things move. And so sometimes it'll seem like we're restating some things that we talked about before. And so there is a little bit of overlap, I guess is what I'm trying to say. But we need to cover them separately so that when we're done, you will see how they all fit together in a bow and describe how things move, all right? So I'm going to read Newton's law of motion. These are my words. They're probably very similar to whatever you have in whatever textbook you're using or whatever on the internet you could look up about Newton's first law of motion. I'm not going to write it down because usually you never refer back to the words anyway. I'm going to read it to you. We're going to say it several times. And by the end of the lesson, you're going to understand in your bones what it actually means, which is much more important than memorizing these words, okay? Here we go. Newton's first law of motion, very simple to understand. Objects at rest will stay at rest unless they're acted upon by an outside force. That's sentence number 1. Objects that are in motion will continue to stay in motion in a straight line unless acted upon by an outside force. Okay, 2 sentences. Now I could write them down, but it'd be a bunch of words and it doesn't matter. Let's just say it one more time and we're going to talk about it, understand it. If an object is at rest, it's going to stay at rest unless it's acted upon by an outside force. And an object in motion that's already moving will tend to stay in motion in a straight line unless it is also acted upon by an outside force. So there's a lot of talking in this lesson, not very much math, and we're going to, I'll draw some pictures in a second, but ultimately it's a lot of talking, and that's okay. Sometimes the deepest fundamental things that we have to understand just comes about by talking. That's how we get the point across, all right? So let's break this down. An object at rest, what does that mean? Right, so I can have a crate here, and I can say it's at rest. And it's when I say it's at rest, this is the ground. Okay, so we just walk up in the forest and you find a crate or some box or something, an apple sitting on the ground. It's not moving. You stand there and you look at it. All right, what Newton's law is saying is that that object, when it is initially at rest, it's going to stay at rest unless some force comes along and pushes it. That's very simple to understand, okay? But sometimes the simplest things are the most core fundamental things that we have to have in our brain. So what would cause that apple or that crate or whatever it is in the forest to actually move? Well, the wind could come and blow it. That would be a force. That would be moving it from its initial place at rest. All right? It could be an earthquake shaking the ground. That would be a force. That would cause it to move. I could go over and I could kick it. That's a force. You know, you get the idea. A squirrel could come along and start eating it and rolling it around. Those are forces. So if you literally never exerted a force on that object that was at rest, it would literally stay at rest forever. It would never move, right? So an object at rest tends to stay at rest. That just means it won't move unless acted upon by an outside force, right? That's sentence number 1. Now, I could go into deep space and I could have some kind of cannonball or something like that, and I could shoot this thing, out of this cannonball, right? Like this, and this thing is traveling with some velocity v, it's going to the right. Now, if we go in deep space, why am I choosing deep space? Because there's no forces, there's no wind, there's no earthquakes, there's no birds, there's no people, and there's no gravity either if we're in deep space. I'm talking about outside of our galaxy, okay? You happen to float your spaceship up and you notice that there's this object traveling through deep space. It's traveling with some constant velocity and it's going in a straight line. That object will continue to go in a straight line forever unless acted upon by an outside force. You could literally cruise right next to this thing and just watch it traveling with it for thousands and thousands and thousands and millions and billions of years, and it will never move unless it's acted upon by an outside force. What kind of force could act on that thing? Well, I could bump it with my ship, right? If I bumped it with my ship, that would impart a force and it would it would not be traveling in a straight line anymore, right? So an object in motion will tend to stay in motion unless acted upon by an outside force. I could shine a very high-powered laser on it. That would, we're getting into momentum here, but that would impart a little force which could push it and change its trajectory. But the idea is that objects are going to travel in a straight line unless acted upon by an outside force. Now, in our solar system, when we shoot a space probe, of course, the trajectory is always curved, but that's because the gravity from the sun is pulling on it, exerting a force. But when we're away from any forces, things always want to travel in a straight line. And here's the critical thing. When an object is traveling in that straight line, think about that cannonball in deep space. It's just cruising along, and I'm cruising right next to it, looking at it. And there is no force acting on that thing, but it is still traveling in a straight line. So in other words, forces are not required to maintain the state of motion. There is no force required to get that ball to continue moving. Once the object is moving, no forces are needed or necessary. The object just keeps moving forever. In our universe, things just keep moving. And if they're already still, they're still moving. It's just that they're moving with zero velocity. So it's really the same law, right? When you think about it, an object in rest tends to stay at rest. An object in motion tends to stay in motion unless acted upon by an outside force. So you could kind of boil the whole thing down just to say that objects always continue moving in a straight line unless acted upon by an outside force. It's just in the case of an object at rest, its velocity is zero. So of course it's going to maintain a zero velocity forever. And if its velocity over here is 15 meters per second, it's going to maintain a 15 meters per second velocity forever. No force is required to maintain the motion. You see, because in the early days, before Newton, people thought that forces were needed to maintain the motion, to keep the motion going. That's what people thought. Newton came along and said, no, no, no. Once the thing is moving, there are no forces necessary to keep it moving. Forces just tend to change the state of motion. All right? So that's why I'm going to write my first words on the board here. I'm going to put it in all capitals. Forces do not cause motion. And then under this, I will say forces cause objects motion to change. Triangle means change. So I'll put a little exclamation point right here. This is a critical distinction. All right. This is actually the main impetus, the main thrust, no pun intended, of Newton's first law of motion. Prior to Newton, people thought that objects that were moving, like on the Earth here, that forces were required to maintain their motion. Think about pulling a box on the ground, on the grass or on the carpet. I have to pull that box. As soon as I stop pulling, the box stops. And then I want to move it again, I got to pull it again. But as soon as I stop pulling, it stops. So that conditioned people to believe that when things move, you must be constantly maintaining some force. But we now know, and I'll draw a picture in a minute, that the reason it stops is because there's a force acting on the box called friction. That is why the box stopped. If there's no friction, then the box actually would keep moving on forever. Think about the case of an icy lake, a frozen lake. You grab a puck or something and you slide it just with one little push, you let go, you're not touching it anymore. Of course, it goes on and on with very low resistance to motion, very low friction, so it goes on and on and on. And if you reduce the friction all the way to zero, it goes forever and ever in a straight line, right? But in everyday situations, when we pull things or push things or whatever, they generally stop because there's almost always friction acting in the real life, but friction is a force. So the object tends to want to continue moving once we get it started, unless it's acted upon by an outside force. So forces do not cause motion. That just means that once the motion is going, we don't need a force to continue the motion. That's what that really means. Forces cause objects' motion to change, right? If the object's at rest, a force will change its state of motion from rest. It'll start it moving, right? If an object's already moving and I apply a force to it, it's going to speed it up or slow it down or change its direction. Either way, I'm changing its state of motion. So forces cause objects' motion to change. But what is a change in motion, right? What is a change in motion? This is another way, this sentence right here is another way of saying forces. cause acceleration. Right? Acceleration. That's what they do. Because acceleration is a change in motion. That is the definition of what a change in motion is. I mean, what is acceleration? It's the change in the velocity divided by the change in the time. How many meters per second I go up or down over how many seconds. I'm speeding up or I'm slowing down. And also, we're going to learn that this change in velocity, it doesn't necessarily need to be speeding up or slowing down. A change in velocity also counts if you change directions. If you're going this way and now I'm moving this way, I have now changed my velocity also. So forces cause acceleration. That's what they do. They don't cause motion to happen, or they don't cause motion to be, they're not required to maintain motion. Forces simply, when they act on an object, change the state of motion of the object. They cause an acceleration. And that's kind of dovetailing into Newton's second law, where we write down that force and acceleration are related to each other. But right now, in words, forces cause acceleration. They cause the object's motion to change. All right? So let's go back to the picture that people, used to talk about when we did the thought experiments about this. And what we'll do is we'll put a crate on the ground like this, just on some grass or rocks or carpet or whatever. And you pull this way with some force like this. Well, if I pull it this way and let go, it stops. If I pull it this way again, let go, it stops. It appears in everyday situations that I need to continue pulling on the thing to get it to move. That's why people thought forces are required to maintain the motion. But now we know that what's actually happening here is the rubbing that's happening here we call friction. And so there's always a frictional force that's basically running counter. If I'm pulling this way, the frictional force is trying to oppose the motion. So you see, forces do not cause motion, even though it appears to happen here. What's really happening is I'm pulling, but you see, forces, objects in motion tend to stay in motion unless acted upon by an outside force. As soon as I stop pulling, the outside force of friction stops the block. That's why it stops. And that fooled everybody for a long, long, long time until Newton codified it into his first law of motion and said, no, no, no. When objects are moving, they continue moving with no forces on their own forever in a straight line. There must be a force to change that state of motion. In this case, the force that stops the motion is the frictional force. But if there was no frictional force, then you would literally, once you terminated this pulling force, the thing would move forever and ever, just like it slides across a lake, frozen lake, or in deep space. All right, so now we need to transition to talking about the second part of this, which is kind of basically related to what we've already said, which is called the word inertia. So I'm going to write that word down, inertia. All right, again, I'm not going to write a definition of inertia because you're never going to look it up. I'm going to tell you what inertia is. Inertia is the tendency or the propensity for an object to remain at rest or to stay in motion. Basically, inertia is the resistance to something changing its motion. Let's take two situations. First of all, let's go back into deep space. Let's do a thought experiment. We're in deep space. We're nowhere near any galaxy or anything. We're literally in the middle of nowhere. And there's two objects in front of you. The first object is a golf ball, little bitty ball about this big. Right next to it is another object that is a car, like an automobile. You pull it from Earth, it's floating, they're both floating in space. Which one has more inertia? Well, the car has more inertia. Inertia is the measurement of the resistance to motion, the resistance to change its motion. If I go up to that ball and push on it with some known force of, let's say, 1 Newton, it's going to fly away. And it's going to go in a straight line forever and ever, even after I'm not pushing it anymore. Newton's first law. But then I go to that car and I push it with 1 Newton. It's going to start moving, but it's going to resist my motion. Just think about being in a swimming pool when you're floating and you have, an adult try to push on them when they're floating. It's hard, but when you push a child, it's easy to move them around, right? This has nothing to do with gravity. There's no gravity anywhere. We're in the middle of nowhere, in between the galaxies, thousands and millions of light years away. But that golf ball, when I push with a 1 Newton force, is going to start moving rapidly. When I push on that automobile, the car, it's going to resist my motion, but it will start moving, and eventually it will accelerate away. And then, of course, it'll coast forever and ever away, at some known speed away from me. So those two things have different amounts of inertia. And what we're going to learn, and what we're learning right now, is that basically mass gives rise to what we call inertia. If an object has more kilograms of mass, it has more inertia. That means it's going to be harder to get it to move, right? If it has fewer kilograms of mass, it's going to be easier to move. This has nothing to do with gravity. We are nowhere near a gravitational field. The intrinsic amount of matter inside of something tends to cause the object to resist its state of motion. If it's already at rest, it's going to be harder to get it to move if it has a lot of inertia. If it's already moving at a high rate of speed, it's going to be harder to change its motion, to get it to speed up or slow down if it has a high inertia, high mass, right? And so what is mass anyway? It boils down to protons in the nucleus of the atom, neutrons. They both have a relatively high mass. Electrons are very small mass, so electrons don't really contribute much to the mass of the object, but a little tiny bit. Protons and neutrons in the nucleus of the atom, that is most of the mass of an object. So if you have something made of lead, those lead atoms have more protons and neutrons, so it's a more massive object than something made of carbon, let's say. Less protons and neutrons, and so it's going to have less mass. All right? So when we say something has high inertia, we're just saying that it's harder to get it to start moving to change its state of motion, or if it's already moving, it's harder to deviate its motion, to change its direction, or to change its velocity. All right, the next thing we need to talk about is what we call the net vector force. It sounds complicated, but I promise it's really not. Let's take two situations. Here is my crate resting on the ground. It's at rest, which means the velocity is equal to 0. It's not moving at all, okay? And then let's take another situation right next to it. Again, we have maybe a second crate separate from the first, and it's sitting right here as well. All right? Initially at rest, here it is. No force is acting on the thing. It's going to stay at rest forever and ever and ever. Its velocity will be 0 meters per second because Newton's first law of motion says that the object at rest will tend to stay at rest unless acted upon by an outside force. So we expect it to stay at rest forever. Now, let's take that same situation over here, initially at rest, and let's apply a force to it. Now, if we apply a force in this direction, we'll call that F1, right? Then, of course, we expect the box to start moving. It's not going to be at rest anymore because we're applying a force, and of course, the force is going to tend to move the object. If we then remove the force, then the frictional force will slow this thing back down to rest again, okay? But instead of applying one force to only one side of the block, let's say it's initially at rest, and I apply two different forces to this block, both equal and opposite, and I'll call this force number 2. So I'm literally going to take this box and like squeeze it between my fingers. Just imagine. I mean, I could just take this little magnet right here. This thing is at rest right now, okay? Now, if I push it, of course, it's going to start moving, right? But what if I apply a force to both sides, equal and opposite? Okay, you see, if this force is bigger, then of course it still moves this way. If this force is bigger, then it's going to move this way. But if the forces are exactly the same, then the thing doesn't move at all. So what I'm trying to say is if the force number 1, the vector number 1, we call force, when we add it to the vector force number 2, if that equals 0, then it stays at rest. So I guess I wanted to point out, because the law of motion says an object at rest will tend to stay at rest unless acted upon by an outside force. And then a lot of people say, well, wait a minute, there's forces here. Why didn't it move? Well, it's because when we say acted upon by an outside force, what we're saying is if multiple forces are acting, it's the net force acting on the outside of the thing. If an object has a net force different than 0, then it will change its state of motion. So what we could do is rewrite Newton's law. We could take some creative license and we could say an object at rest will tend to stay at rest unless acted upon by a net force, a net external force. So if we have two forces, the net force here is 0. When you add these vectors, one is in one direction, one's in the other direction, they're negatives of each other, it's 0, so the thing stays at rest because the net force on the outside is 0. So it's not so much that there's a force on the outside, it's that there has to be a net force that is different than 0, then of course the thing won't be at rest anymore. Now let's take the same sort of situation, but instead of being at rest, let's take this object and let's You know what? Let's see here. Let's do it in deep space. Let's not put it on the ground. Let's not do that. Let's do it like this. And then let's say that this object is just traveling forward at a velocity of 10 meters per second. So it's moving this way. So we know from Newton's law of motion, Newton's first law, this thing is going to go at 10 meters per second forever in deep space unless acted upon by some kind of outside force. So it's just going to keep on moving. So let's draw this thing again, some snapshot in time later, where it's now over here. It's moved from here to here. And what is the velocity? It's still 10 meters per second because, you know, no forces have acted. Now let's say that I float up to this in my spaceship and I'm on the spacewalk or whatever, and I apply a single force to the outside, like this. Single force. What's going to happen? I'm going to accelerate this thing to something faster than 10 meters per second because it was traveling at a constant rate of speed. Now I apply a force like a booster, like a rocket booster on the back, and it speeds it up. Okay. But so of course that's a external force, a net external force that's going to change its state of motion. Okay. But what if I actually do the following? What if I put a rocket booster on the front and a rocket booster on the back? In other words, I have a booster pushing it this way, and then I have a booster on the front pushing it in exactly the opposite way, right? Then the same exact thing happens. If force number 1 plus force number 2 is equal to 0, and when I say plus, I mean the vector sum of these forces. If this is the same, then it stays in motion. In constant motion at 10 meters per second. So the way to illustrate this is if I have my little ship right here and you got to use your imagination. Let's just say that it's moving at a constant velocity this way, and I float onto it and I start pushing on both sides. It's still going to maintain its 10 meters per second because the net external force is still 0. So the second part of it, an object in rest tends to stay at rest unless acted upon by an outside force. An object in motion tends to stay in motion unless acted upon by an outside force. It's really unless acted upon by a net force on the outside. It's not just that there's a force here. There has to be a net force, a net vector sum. In this case, there's a 0 force as a vector sum, so nothing changes. So you have to have, that's why rocket engines are always on the rear end of the rocket, because you want to cause an acceleration of the thing. So the net force acting on an object is actually what matters, right? So this is a a good bit of talking to describe what we now consider to be very simple. But you got to remember that before Newton put these laws down, there was no spaceflight. No one saw pictures of people floating in space. You have all seen pictures of people floating and throwing pencils and pens, and you can easily understand how things move in space, right? And so it's easy for you to visualize what's happening. But before they had this, all they had was things on Earth. You throw a ball and you stop the force of your hand, and the thing comes crashing down, the motion stops. Hits the ground, the motion stops. You pull something across the carpet, stop pulling, it stops. You're running, you stop exerting that force, it stops. So it appeared for a long time, for thousands of years, that forces are required to keep motion moving. But Newton came along and said, no, no, no. Motion is something that always happens. Things are always wanting to move. We're always wanting to move in a straight line with a constant velocity. If they're at rest, it's just that their velocity is 0, so it always wants to stay at rest. It's really the same law, really, with the velocity being 0 if the thing is at rest. It always wants to move at whatever velocity it was. Forces do not cause motion in the sense that they're not required to keep the motion happening. Forces cause the motion to change, which we have a word for. Forces cause acceleration. And so that is what Newton's first law says. Inertia, the more mass something has, the harder and the more it resists your motion. And so mass is basically a measurement of how much it resists the motion. So we're going to wrap these ideas up and kind of continue working with them when we talk about Newton's second law of motion in the follow-on lesson. So for now, watch this a couple times. Make sure you understand it. Follow me on to the next lesson. We'll continue talking about Newton's laws of motion.